A short video in the vector calculus package. This was on how to do some operations with vector and vector fields. It will be useful for our next topic, which will be differentiation. Let's get started. The first operation we're going to do is calculate the norm of a vector. A reminder, we need to load the vector calculus package, and we also need to set the coordinates to something Cartesian, cylindrical, or spherical with the components of that system. So calculate the norm, we use the double vertical bars, V. As you can see, it assumes that all the components are not complex. The other way to do it is to use the actual norm procedure, which is in the vector calculus package. Now let's remind ourselves how to do a dot or scalar product. Here are two vectors written by A and B. To do the dot, we do A, and then we look for in the palettes either the large multiplication sign, or we can use a period. Let's use the large multiplication sign, B, oops, and it does that calculation. The other way to do it is to use the period. Using this technique, we can, with the square root button, use A dot A, and you will see, if you noticed, that when I put the period, it actually turned it into a vector sign, and this allows us to calculate the norm of the vector. Calculating the norm of vector is useful because it allows us to calculate the unit vector of a vector. So let's use A, and let's put a little hat over it, and that's called equal to A the vector, and then we're going to divide by the magnitude or the norm of A. And as you can see, it properly calculates. Here's the x component, the y component, and the z component of this unit vector. The other way to quickly calculate the normalized vector is to use normalize. Now comes the question, what if you need to do the dot product of non-Cartesian values? Well, if you do that, it will not work. As you can see, this does not work. The biggest issue here is it needs to be Cartesian coordinates or a rooted vector. Since most of the physics we do are free vectors, that means we can move them anywhere. I find the best way to solve this problem is to convert everything into Cartesian coordinates and then do the problem. So here we mapped to the Cartesian coordinate system, and it has done the appropriate calculations necessary to choose the x and y and z component, given the fact that this was in cylindrical coordinates. And now using the v1c and the v2c, i.e. v1, v2 in Cartesian, it can do this particular calculation. The alternative is to root your vectors, but again, most of the time we use free vectors. Can we dot vector fields or vector fields with vectors? And the answer is yes. And can we dot a vector with the vector field? Sure, why not? This will be different when we get to cross products. So the last technique that we need to cover is the cross or vector product. This is the product that produces a vector. Here's a reminder of what the A cross B looks like. So how do we do the cross product? Now, surprisingly, we write out our vector, and we go to the palettes. We use the cross product operator, and it calculates the appropriate values for the components. Alternatively, we can use the cross product procedure. And if we define D as B cross A, not surprisingly, we find that A cross B is equal to minus B cross A. And finally, if we wish to visualize these vectors, again, I prefer to use plots arrows as opposed to the plots vector procedure within the vector calculus package. Here's A, here's B. Let's do C as A cross B. And again, you can see A, you can see B, and C is the one up in the vertical direction. Can we do cross product of vector fields? And the answer is yes, because the vector is defined everywhere. Let's define G as the cross product of vector field F1 and F2. And again, you get a vector field out of it with the components of the other two vector fields. Can you cross a vector field with a vector? And the answer is no, because the vector is a free vector and we're doing it with a vector field. So we define a root as a rooted vector, then calculate the rooted vector with the components of the vector field and our a root. And if needed, we can then convert this rooted vector back to a free vector by using the convert vector procedure. Hopefully you made it through all of that. And hopefully it was a reminder from the techniques and operations from the videos on vectors. It's useful because we'll use it for the next topic, which will be differentiation in vector calculus.